Welcome back. In part 1, we covered decision trees and random forests. Today, we're taking things to the next level with boosting. Instead of building trees in parallel, boosting builds them sequentially, where each new model learns from the previous one's mistakes. We'll explore two heavyweights, AdaBoost and gradient boosting, and show you how to implement them in scikit-learn. We'll also dive into XGBoost, the champion of machine learning competitions. It's all about turning weak learners into powerful ones by focusing on improvement. This principle works in life too. Focus on your weaknesses, and you'll become unstoppable. Let's dive in.
When sampling is performed with replacement, this method is called bagging, short for bootstrap aggregating. When sampling is performed without replacement, it is called pasting. In machine learning, bootstrap refers to sampling the data with replacement. The term actually comes from the phrase pulling yourself up by your bootstraps, meaning building something from limited resources. And that's exactly what we do here. We repeatedly sample from the same dataset to create multiple slightly different datasets. The following code trains an ensemble of 500 decision tree classifiers. Each is trained on 100 training instances, randomly sampled from the training set with replacement. This is an example of bagging. But if you want to use pasting instead, just set bootstrap equals false. The bagging classifier automatically performs soft voting instead of hard voting if the base classifier can estimate class probabilities. Instead of building a bagging classifier and passing it a decision tree classifier, you can instead use the random forest classifier, which is more convenient and optimized for decision trees. With a few exceptions, a random forest classifier has all the hyperparameters of a decision tree classifier to control how trees are grown, plus all the hyperparameters of a bagging classifier to control the ensemble itself. So keep in mind that in random forest classifier, each tree is built independently and in parallel, using a different subset of the dataset. These subsets are generated through either bagging or pasting, and the final prediction is obtained by combining the individual trees' outputs using majority voting for classification or averaging for regression. Here's a detailed comparison of the single decision tree on the left, which shows signs of overfitting by creating complex and intricate decision boundaries to fit the training data, and the random forest with bagging on the right. The single tree's decision boundary is characterized by sharp, jagged edges and small, isolated regions, indicating that the model is capturing noise in the data. In contrast, the random forest's decision boundary is much smoother and continuous, indicating that the model has generalized better and is less likely to overfit. This smoothness is achieved by averaging the predictions of multiple decision trees, which reduces the variance and leads to a more robust and generalized model. Now, so far we've only been talking about sampling the rows in our data. You know, the different training instances. But you can apply the exact same logic to the columns or features, and that leads to some really powerful advanced methods called random patches technique. It's super effective when you're dealing with really complex data that has tons of features, like images. This is the code we previously used for applying the bagging method. As shown in this table, we used 500 decision trees. Each tree is trained on a subset of 100 samples drawn from the dataset, with replacement. Since we did not specify the max_features parameter, it takes its default value, meaning that all features are used when building each tree. Now, if we want to switch to the random patches method, we need to modify the code slightly. Setting max_samples equals 1 means that each tree uses the entire dataset. If we reduce this value, for example to 0.6, then each tree is trained on only 60% of the samples. By setting bootstrap equals false, we switch from bagging to pasting, meaning that sampling is done without replacement. We also set max_features equals 0.5, which means that each tree uses only 50% of the features. Finally, setting bootstrap_features equals true means that features are sampled with replacement. High bias means the model is too simple and cannot capture the true pattern, while high variance means the model is too sensitive to the training data and may overfit. In an ideal world, we would like to have both low bias and low variance, but in reality, achieving both simultaneously is very challenging. Bagging and pasting are mainly designed to reduce variance by training models on different subsets of the data. Bagging uses sampling with replacement, which increases diversity among models, and typically leads to a stronger reduction in variance. Pasting, on the other hand, samples without replacement, resulting in slightly less diversity, and therefore a smaller reduction in variance. In both methods, the effect on bias is usually minimal, and depends on the model and dataset. Yet another great quality of random forests is that they make it easy to measure the relative importance of each feature. Scikit-learn computes this score automatically for each feature after training. Then it scales the results so that the sum of all importances is equal to 1. You can access the result using the feature_importances_ variable. There are situations where we might want to reduce the number of features in our model. For example, we might want to improve interpretability by including only the most important features. In scikit-learn, we can use a simple two-stage workflow to create a model with reduced features. First, we train a random forest model using all features. Then, we use this model to identify the most important features. Next, we create a new feature matrix that includes only these features. In our solution, we use the select-from-model method to create a feature matrix containing only features with an importance greater than or equal to some threshold value. Finally, we created a new model using only those features.
So far, we improved our model by combining many trees and letting them vote, like in random forest. This helps reduce variance and makes the model more stable. But there's still a limitation. What if all these trees are still making similar mistakes? Instead of building many independent trees, what if we build them sequentially, where each new model focuses on correcting the mistakes of the previous ones? This idea leads us to boosting. In random forest, trees work independently and vote, but in boosting, trees don't work alone. They learn from each other's mistakes. Boosting is about turning weak learners into a strong learner by learning from mistakes. Let's see how it works.
Boosting refers to any ensemble method that can combine several weak learners into a strong learner. The general idea of most boosting methods is to train predictors sequentially, each trying to correct its predecessor. There are many boosting methods available, but by far the most popular are AdaBoost, short for adaptive boosting and gradient boosting. And this right here is the core philosophy of AdaBoost. See step 1? Every data point starts off with the same level of importance. But after that first model gives it a shot and messes up on a few points, look at step 2. The misclassified points get bigger. They've literally been given more weight. So in step 3, the next model is forced to pay way more attention to them. This process repeats. And by the end, in step 4, you have a final decision that's a weighted vote from all the models, where the more accurate models get a bigger say. In scikit-learn, we can implement AdaBoost using AdaBoost classifier or AdaBoost regressor. The most important parameters are n_stimators, learning rate, and loss. In AdaBoost, the learning rate controls how much each weak learner contributes to the final model. A smaller learning rate means each estimator has less influence, so the algorithm learns more slowly, but often more reliably. A larger learning rate makes each estimator more aggressive, which can speed up learning, but also increases the risk of overfitting. That's why a common strategy is to use a smaller learning rate together with more estimators, to get a better balance between accuracy and stability. Another very popular boosting algorithm is gradient boosting. Just like AdaBoost, gradient boosting works by sequentially adding predictors to an ensemble, each one correcting its predecessor. However, instead of tweaking the instance weights at every iteration like AdaBoost does, this method tries to fit the new predictor to the residual errors made by the previous predictor. Let's see this in code. First, let's fit a decision tree regressor to the training set. Next, we compute the residuals, the difference between the true values and the predictions of the first model. These residuals represent the errors that the first model failed to capture. Instead of training the next model on the original targets, we train it on these residuals. In other words, the second model is not trying to learn the full problem again. It is specifically focused on correcting the mistakes made by the first model. We repeat the same process again. The third model is trained on the remaining errors from the previous step, focusing on what the earlier models failed to learn. Finally, we combine all the models together. The prediction is simply the sum of the outputs from all the trees. So instead of relying on a single model, we build a strong predictor by adding up multiple weak learners, each one correcting the mistakes of the previous ones. Instead of implementing all these steps manually, we can use gradient boosting from scikit-learn. By setting using underscore estimators equals 3, we are telling the model to build 3 trees sequentially, just like the 3 steps we implemented before. And the learning underscore rate controls how much each tree contributes to the final prediction. So under the hood, this single line of code is doing exactly the same process, learning from errors, step by step, and combining the results into a final prediction. And here's the result. The first predictor is trained normally. Then each consecutive predictor is trained on the previous predictor's residuals. The right column shows the resulting ensemble's predictions. It is worth noting that an optimized implementation of gradient boosting is available in the popular Python library XGBoost, which stands for Extreme Gradient Boosting. This package aims to be extremely fast, scalable, and portable. In fact, XGBoost is often an important component of the winning entries in ML competitions.
Thank you so much for staying with me until the end. In these 2 videos, we covered a wide range of important concepts, from overfitting and how to control it, to ensemble methods like bagging and pasting, and finally boosting. If you found this content useful, please support the channel by liking the video and subscribing. And don't forget to share it with others so more people can benefit from it. Stay tuned for the next video, where we'll dive deeper into another exciting topic. Until then, see you in the next one.